Hi guys, we're going to have a look at sketching tan graphs today. Tan's a very interesting animal, quite different from sine and cos, so let's have a look at that and see if we can have some fun together. Okay, now what I'm going to do is I'm going to create the graph of tan for you from the unit circle. So I'm going to use this little unit circle here, and I'm going to increase the angle that we make with the positive direction of the x-axis, and you're going to see tan tracing itself on this pink curve, where the horizontal axis represents the angle which we make, the angle which we are creating in here as we sweep around in an anti-clockwise direction firstly, and then in a clockwise direction, anti-clockwise from 0 to pi, and then clockwise in the negative direction from 0 to negative pi. And as you know, that the ratio of tan is opposite over adjacent. So I'll show you as we just explore this, and you'll see something really amazing unfold, and then you'll understand why we have asymptotes in tan. Now there's the first one there. Okay, so what I've done is I've created a little bit of an angle, and you'll notice that for this angle, which was represented by this horizontal distance in this direction on this horizontal axis, we've created a little blip for tan. Okay, and we'll do another one now. Okay, now there's tan there for this particular angle in here, which is basically we've displaced ourselves horizontally on the theta axis, if you like, by this far to represent this angle in here. Here's another one. Okay, so now what I wanted to illustrate to you now is that basically tan is opposite over adjacent for this angle here, which is red line over blue line, right? Now, by some very clever skullduggery here, what I've done here is I've created some similar triangles. Now see this green line here, this vertical green line, that exists in a triangle which I'm about to trace out here, like this. Right? Now, the green line is basically it exists in a triangle which is similar to our unit circle triangle because first of all, this angle in here is a shared angle, and this angle here, that angle there, and that angle there are right angles. So therefore the third angle here and here must be the same, and therefore the triangles are similar, therefore they are identical in shape. Right? Now, this is the clever little bit here. Why did I create this triangle with the green vertical line in it? Well, actually I didn't create it, somebody else did, but it's jolly good. Now this green line, this ratio of the green line over this distance here, which is 1, being a unit circle, so this basically means that this green line gives you a vertical line depiction of the value of tan, because it's the ratio of this line over 1. So therefore the height of this line gives you the direct reading of the value of tan. Okay? And you'll see as we go along, we're just stepping it through here, this green line will be the same height as the little blip on the pink tan graph. Okay? Now the green line just gives you the size, it won't give you a minus or a plus, that'll come later, but it does give you the size. Okay? And in quadrant 1, tan is positive anyway, so that the position of the end of the green line is coinciding with the vertical height of tan. Okay? Do you get me? Very good. Okay, here we go. Now here's another one. Here, look, a bigger angle, and now see how tan is rocketing off into asymptote land, you see? And as this angle in here gets bigger, you will see that when we get to 90 degrees, there's no blue line left. So you've got red line divided by 0, which can't happen. That's why it's undefined. That's why you get an asymptote. Okay, there it is. Now, next one. Okay, now we're really getting off the scale now. Tan's right up here somewhere. Okay? Yeah, next time it'll be undefined. It is undefined. Okay? And this time we've got ourselves, now when we get into quadrant 2, where tan is going to become negative, because you've got opposite, a red line positive opposite over a blue line negative adjacent. That's why it's negative in quadrant 2. Let's do it. Now you'll notice that this is the size of the green line, and you'll notice the tan is coming in from the asymptote land in the negative, okay? So basically this is the discontinuity at the asymptote here at 90 degrees. It goes off into positive infinity, and then just immediately past the 90 degree mark, it zooms in from negative infinity because it's now minus in quadrant 2. So as I step through the angles between 90 and 180, you'll see tan will gravitate its way back here to 0. There it goes, there it is, there it is. See, there he is, Mr. Tan, following the green line. And Tan the man is coming in for a landing. There he is. And that was pi. Now we're going to go in the negative direction round this away, right? Round that away, okay? Have a look. There it comes. Now, yes, now where are we? What angle have we got? We've got a negative angle here, so we're going back in the negative, so we're going over this away in terms of the angles, into the negatives, and we've got a negative angle there, the height of which is the same as the height of the green line. Yes, you're getting this, aren't you? Okay, step away, and we're going into almost asymptote land, and there it is, undefined there. Now, that was quadrant. What quadrant was that? That was, goodness, wait a minute, that was this quadrant here. Yes, and tan is negative in that quadrant. Now, when we get into this quadrant, tan is going to be positive. Positive. Now, why is that? Because it's got a negative red line over a negative blue line. Negative over negative gives you a positive. So let's see if that works out. Yes, here it's coming in here. Look, as the angle gets more negative, it's moving over this away, horizontally over that away. But it's still positive, and it's going to come in for a landing when we get to minus pi. There it is. You get it? Apple of my eye. Mr. Minus pi. There you go. See, it's good, isn't it? It's a nice little graph, this one. It shows you exactly what tan the man is doing. And the asymptotes are at the verticals, that's 90 or pi on 2, and 270 or 3 pi on 2, or minus pi on 2, whichever way you want to look at it. Now we're going to do some properties of tan. Here they are, properties of tan. Now this graph here I've just shown you from 0 up to 2 pi, which actually includes 2 periods, right? I haven't given you the minus and the plus thing as I did in the previous screen angles. But yeah, so one period would go up to here, including the asymptote, and then from here to there. That is one period, right? So you can see that tan does not have a period of 2 pi. Tan x, or tan theta, it just has a period of 1 pi. Yeah, period is pi. Yes, the asymptotes are at pi on 2, and then every period after that, positive or negative, right? And the period is pi. So, yes, makes sense, doesn't it? Good, ranges are, that's right, because the range goes from minus infinity up to plus infinity, doesn't it? And when x is 0, tan of x is 0, and when x is pi on 4, that's a point of scale for you, nice convenient one. When x is, or theta, whatever it is, when x is pi on 4, we have 1, because tan of pi on 4 or 45 degrees is 1. Yeah, good. Now, if you have y equals tan nx, okay, n, the period will be pi over n, not 2 pi over n, just pi over n for tan, different from sine and cos. There's your point of scale there. There's, yes, that point there. You can see what we're doing. We've got our bearings now, and we're going to go and do some step-by-step process for sketching tan graphs, which is very laborious, just as it is with sine and cos. But however, we need to know what the recipe is. It's pretty much the same as sine and cos, except there are some differences, like the period's different. You have to work out what the asymptotes are, and you don't need to do a quarter cycle span either. Just so it's essentially the same as sine and cos, and the differences are that you don't have to find the amplitude because it doesn't have an amplitude, or a quarter cycle span, and you do have to find the asymptotes. Yes, you do. Okay, so here's one. Here's one for us as an example. It's got a dilation, a y dilation of a factor of √3, or from the x-axis. It's got a period of pi. It's got a vertical translation of 1 unit up. And now, What I do need to say to you guys is this. Unlike sine and cos, when a graph of tan is translated vertically, the distance for any value of y, the distance between the x values in successive periods are still exactly the same. Exactly the same horizontal distance apart. Now, this is because of the nature of tan, because it repeats itself exactly, and it's sort of discrete, doing exactly the same shape from one period to the next, but being discontinuous, unlike sine and cos. So this means that if you found one new x-intercept of a vertically translated graph, then all the other intercepts can be deduced from their corresponding untranslated equivalents, because you will know how far they are apart. They're one period apart, okay? And you can just work out by working one new x-intercept or y value in relation to the other untranslated graph. You can work out by horizontally shuffling to the right or left what all the new corresponding x-intercepts are going to be. You can't do that with sine and cos, because with sine and cos the distance between the x-intercepts changes with vertical translations, but it does not with tan. Here's a step-by-step process for you. We deduce the transformations from the graph equation. We calculate the working domain. That's completely the same as sine and cos. We calculate the equations of the asymptotes. That's different. We calculate the transformed starting point. That's the same. We calculate the coordinates of the endpoints, same. Calculate the x-intercept, same. Calculate the y-intercept, same. Then we draw in all vertical asymptotes using dotted lines and clearly label them with their equations. That's obviously different. And then we start at the coordinates of the transformed starting point, and we sketch the graph. I sketch it in half-cycle segments, okay? Half-cycle segments. From the central point of inflection, if you like, then up to one asymptote, and then from the same point down to the other asymptote within which it resides, okay? Each cycle of tan is sandwiched in between two asymptotes. So number 10, we add a point of scale. Yes, that's because you need to add a point of scale with tan in nearly all cases, because you need to have some way of expressing whether or not there's been a vertical dilation or not, okay? That's a little bit different from sine and cos as well. And lastly, you check that all endpoints and x and y intercepts are appropriately labelled, and usually as coordinate points, okay? And you label the graph with its equation, and then we're done. Yeah, we'd want to be, wouldn't we? So there's the equation we started with before. Let's have a go at it, shall we? Transformations refer to above, as we were saying before. The working domain, okay? So the working domain, if x goes from... Oh yeah, well, it's just a normal old working domain, this one, because x hasn't been fiddled with. The term behind the tan has not been messed with. It's just the usual original base model template version of x. So therefore the working domain is going to be exactly the same as the domain, 0 to 2 pi. Apple of my eye. And here's the asymptotes for you. They will be pi on 2 plus every pi forwards or backwards from that point. So x will be, in this case, pi on 2 and 3 pi on 2. They will be the asymptotes within the working domain. Starting point would be, it's been translated up 1, so it would be x is 0 and y is 1. Endpoints will be 0 and 1 and 2 pi and 1. X-intercepts will be, y, that means when y is 0. So basically we're going to solve that for x, and we get that. So that means if we look at our cast diagram, we've got a basic angle if we were dealing with quadrant 1 of pi on 6, but we're not dealing with quadrant 1. We're actually, we want basically a negative value for tan, negative 1 over root 3. So which quadrants do we want? We want those quadrants, okay, where tan is negative, so we want quadrant 2 and quadrant 4. So in our working domain, guys, what angles do we have in quadrant 2 and 4 which qualify from 0 to 2 pi for that value, for the basic pi on 6 value in quadrant 1? Yeah, they're 5 pi on 6, which is your quadrant 2 value, and 11 pi on 6, which is your quadrant 4 value. So the x-intercepts are going to be 5 pi on 6 and 11 pi on 6. And I've written them there as coordinate points for you. Okay, now the y-intercept, that means x is 0. That'll actually coincide with the left-hand endpoint. That is the y-intercept, so that's going to be 0 and 1. Point of scale, well, I usually use this one, where x is pi on 4. Y would be, what would it be? Root 3 times 1 plus 1, so it would be 1 plus root 3, yes, for root 3 plus 1, which is approximately 2.7, just for graph scaling, making the graph look right type purposes. So there's our point of scale. I think we're ready to go. We would certainly want to be after all that, wouldn't we? So there's our asymptotes. There you have, and there you have. And it's up 1. I usually draw the line of the horizontal equivalent of the central axis for sine and cos, if you like. This is where the point of inflection is in this part of the tan graph, okay, where it starts to, where the bulge going this way meets that, the bulge sort of pointing out that away meets the bulge sort of, you know, this away. There, look, see? It's sort of got a dint in it up here, and it's got a bulge in it down there, if you know what I mean. Yeah, I call this one concave that away, and I call this one concave that away, okay? If you don't understand all that, don't worry. You understand what I mean by the central axis anyway, don't you? Yes, so I've drawn in the line, the y line, where the central axis has been moved to, and then we'll go from there. Okay, starting point there, that's our point of scale, and there's those points there are relevant because they are kind of like where the central axis was. I'm not going to... oh, wait a minute. Oh, no, that's right. Yeah, that's the x-axis there. So there's a half period there. Yeah, half. I'm drawing half periods here for tan. There's another one. There's another one. There's another one. Now we've got to put our x-intercepts in. There they are. Anything else? Endpoints. Yeah, there's the endpoints. I think it's done now. We've got to label the graph, though. There's the graph. Now, I've labelled the asymptotes, haven't I? Is everything good? Yeah. Great. New one. What's this one? Sketch the graph for each of the following. Well, these are pretty easy because these aren't translated up. They do have x goes from minus pi to plus pi, so we've got to work out what they'll look like. But they're not horizontally translated, and they're not vertically translated. This one's sort of an upside down one. But they're not so bad, are they, by the look of them? So let's do A today. There it goes. Now, we've got a dilation of a factor of 3 from the x-axis, and we've got a period of pi on 2, all right? No reflections or translations. Jolly good. Transformations refer above, working domain. Now, if x goes from minus pi to pi, then 2x would go from... yes, minus 2 pi to 2 pi. That will be our working domain. That'll be the domain within which we have to capture our x-intercepts, guys. Okay? Alright, asymptotes. We've got 2x this time, not x, but 2x would be pi on 2 plus k pi, where k is any integer. That means integer, that capital Z. Okay, and you must put that in, by the way, or you get it wrong. Now, so in the negative direction, we're going to make k negative, so that'll get us 2x equals minus pi on 2 and minus 3 pi on 2. Remember, we have to go back as far as minus 2 pi, and that means that's what we get for that in the negative direction. For the positive direction, we say that 2x, and why are we using 2x? Because we've got 2x in here. 2x in here, guys. So 2x will be pi on 2, or 3 pi on 2, therefore x would be pi on 4 or 3 pi on 4. Hence the asymptotes of those, all summarised and beautiful. Okay, starting point. That's, well, because it's not translated up or anywhere else, it's fine. Horizontally or vertically, it's fine. The starting point is 0, 0. Good. End points, and they'll be fine too. Minus pi, 0, and pi 0. This one's a nice easy one, isn't it? Okay. X-intercepts, that means y is 0. So therefore we've got 2x equals 0, and then every period forwards or backwards from there within our working domain. So 2x would be minus 2 pi, minus pi, naught, pi, 2 pi, and therefore x would be that. Yeah, you go, that's our x-intercepts. There's what they are in coordinate form. And the y-intercept means when x is naught, well, that's all right, because that's going to be its normal location, okay? Because it's not translated, the starting point is not translated laterally or vertically, horizontally or vertically. So point of scale, right, therefore 2x will be pi on 4, and y would be 3. And that's because it's been dilated up by a factor of 3. Y would, for a normal tan graph without this 3 out the front, y would be 1, but in this case it's dilated by a factor of 3 from the x-axis, therefore y will be 3, fills us with glee, yippee, and therefore x is going to be, yes, pi on 8, and y is going to be 3. That's our point of scale, guys. There it is. Okay, I think we're nearly ready to go, thank goodness. So therefore, now what have I written here? I've got the point of scale in for you. This is, you can see there's minus pi. There's the y-axis, there's plus pi, and I've got our asymptotes in, minus 3 pi on 4, minus pi on 4, pi on 4, and 3 pi on 4. Yes. Okay, there's all our x-intercepts. This is looking amazing. So that's good, isn't it? Yeah. And what else do we need to do with all this? Endpoints are done because they're the same as x-intercepts, aren't they? Alright, so therefore the asymptotes are labelled, the graph is labelled, and Bob's your uncle. She's done, guys! Yes, and we won. Now this one B, okay, let's do this one. This is, what's this? It's an upside down one. But the good news is that it's not translated vertically or horizontally, so it should be nice and easy for us. Let's go through the routine. Okay, reflection in the x-axis, because it's a y reflection. It's got a dilation of a factor of 2 from the x-axis, and it's got a period of, not pi, but pi on 3. Okay, transformations refer above, working domain. Now, what did I do with that? Oh yeah, so if x goes from minus pi to pi, then 3x, which is what's in here, would have to go from there to there. And that's the working domain we have to use to capture all our x-intercepts, guys. Now, the asymptotes. This time we've got 3x. 3x goes from pi on 2, then forwards and backwards by any number of periods within our working domain. So let's go in the negative direction. We've got this. What have we got to go? Yes, that looks right, doesn't it? Now, do I need to go any further than that? That's 1.5, minus 1.5. So we'd have to go, yes, okay. Actually, it would, wouldn't it? It would need to go for another one, minus... we're going backwards by pi, so minus pi on 2, minus 3 pi on 2, and then it'd be minus 5 pi on 2. Yeah, that's right. I just tricked myself because I didn't. I'd put a stop in there so that it stopped where it shouldn't have stopped. I actually had worked it out. So therefore, x will be that, that, and that. Yes, it looks good. And in the positive direction, similarly, we're going to get that, and therefore we're going to get x is equal to that. So there's all our asymptotes. My goodness, there's enough of them, isn't there? So that's fine. Starting point, yes, good. End points, yes, good. Yes, right, good. Let's keep going. X-intercepts. Now, that's where 3x equals 0 plus k pi, where k is any integer. Goodness gracious, look at them all. That looks right, doesn't it? Because the x-intercept would normally start at 0 and then go forward by every pi and then backwards by every pi within our working domain. So therefore, that's what x is going to be. I think we're nearly done. Y-intercept coming up. Oh, look at them in coordinate form. Gracious me. Y-intercept, yes, normal place, because no horizontal or vertical translations. Point of scale, when 3x equals pi on 4, in this case, and y would be, yeah, minus 2 because of the dilation factor of minus 2 for me and you. There it goes. Yes, is that right? Yeah, so if you divide by 3, you'll get x is pi on 12, and y will be minus 2. So there's our point of scale, guys. Oh, here we go. Goodness, what a busy graph. Let's just figure it all out. There's, alright, there's the point of scale. There's some intercepts in the forward direction, and one of them is the end point. There's the backwards ones in the backward direction, and one of them is the end point, this one. All the asymptotes are put in, aren't they? Yes, so that looks good, doesn't it? Yes, it does. We've labelled them all. Now, we're going to put our equation in, and I think we're done. I think we're done. And what fun! Don't you agree? Oh, well, it's pretty fun, isn't it? Okay, now, you don't sound convinced. Oh, well, come on, you'll get used to it. What's this? Oh, this is a bit of a beast. This is not translated vertically, though, isn't it? Yes? Let's play the sad, glad game. We're sad we have to do it, but we're glad that it's not translated vertically. It's only translated horizontally. Okay? And let's just analyse the thing. Here it is. So what have we got? A dilation of a factor of 3 from the x-axis. And we've got a period. Now, did you notice how I put this in brackets here? That's very essential. You've got to put the two outside a bracket. Then you can work out what the horizontal translation is, guys. Otherwise, you might get it wrong. It's certainly not what it says up here. It's not pi on 3. It's pi on 6 to the right. Anyway, that's yes, horizontal translation of pi on 6 units to the right. Okay? Transformations refer above. Working domain, well, that's a bit of a complicated working domain. So let's just go through this. If x goes from pi on 6 to 13 pi on 6, which is basically a span of 12 pi on 6 or 2 pi, the period of this thing is, the period of this thing is pi on 2. So it looks to me like we are going to get, is that right? Yes, we're going to get 4 cycles of this beast, aren't we? We certainly are. Alright, so let's go. But let's do this. Meanwhile, back at the ranch, we're working our way up to what's behind the tan symbol, to work out where that's going to go from and to capture all our x-intercepts. So, therefore, if x goes from pi on 6 to 13 pi on 6, I'm working my way up to it. Subtract pi on 6 from both sides. Therefore, x minus pi on 6 would go from 0 to 2 pi. Now I'm going to double that to get this expression here. So therefore 2 bracket x minus pi on 6 will go from 0 to 4 pi. Yes? Great. That's our working domain. That's the span of x within which we have to capture all our x-intercepts. And asymptotes, by the way. Alright, asymptotes, here we go. Now, we've got the expression behind the tan sign. 2 open bracket x minus 6 goes from pi on 2 plus any number of repeats in the forward and backwards direction of pi. Now we're going to, basically, we're going to solve that for, oh yes, that's right. Within the working domain, we're going that away. Yes. Now, how far do we have to go up to? We had to go to 4 pi, didn't we? Yes. So that's going forwards. What about backwards? Yes. Oh, no, we don't have to go backwards. What am I talking about? That's all right. We don't have to go backwards. We're just going from 0 to 4 pi. Yes? Sorry about that. So pi on 2, 3 pi on 2, 5 pi on 2, 7 pi on 2. That's 3.5. Then any more than that would be too far within our working domain. So therefore I'm working my way down to what x is for the asymptotes, guys. So I'm solving now from this line here. I'm solving for x. Okay, here we go. There it is. There it is. They are our asymptotes. All right. Starting point. Now that'll be horizontally messed with, won't it? So therefore we know that the normal starting point is when x is 0. So we have 2 times x minus pi on 6 equals 0. Therefore x will be pi on 6. Now when x is pi on 6, there's no vertical translation. So, but there is a. Oh no, that's all right. It'll just be. Yes. It'll go. Y is 0. That's right. Yes, x is pi on 6, y is 0. Yes. I was thinking that there might be an effect of this, but there won't be because it's 3 times 0. That's what I was daydreaming about there. Now, endpoints. Okay, endpoints. When x is pi on 6, y will be 0. There we get that. And when x is 13 pi on 6, y will be 0. We get that. So there are endpoints. We're going really well here, swimmingly. Now, x-intercepts. Here we go. Y is 0. Therefore, we get 3 tan of this thing equals 0. So therefore, within our working domain, we can say, okay, y would normally be 0 from naught, pi, 2 pi, 3 pi, 4 pi. Yes, okay. Now we're going to solve it for x, guys. Therefore, that, you get that, and therefore you get that. And there they are. They are our x-intercepts. Pi on 6, 2 pi on 3, 7 pi on 6. What's that one saying? I can't read it. Whatever it says. And 13 pi on 6, yes? Okay. Alright, so let's go over the screen and get this thing, hurry up and fix it. Y-intercept, so therefore, yes. Oh yeah, this is a very interesting point, guys. X would equal naught. But the fact is that this domain does not include x as naught. It goes from pi on 6 to 13 pi on 6. Therefore, there ain't no y-intercept. Okay? There isn't any. So there. How do you like that? Now for something completely different, no y-intercept. Well, the truth is stranger than fiction. So there, point of scale, I think we're getting to the end now. Point of scale, so when 2x minus pi on 3 equals pi on 4, what do we then get? We get y equals 3 because of the dilation thingy here. Yes, whereas y would normally be 1 when the horizontal is pi on 4, the x is pi on 4. So we'll solve that for x now. There we go. So it's pi on 12. Pi on 12, so there's our 7 pi on 12. Oh, wait a minute. Oh, 2x is... Oh, I'm sorry. 2x is 7 pi on 12, therefore x is 7 pi on 24. Now I'm getting it. I'm mumbling and bumbling because it's Sunday morning and I'm tired. So, sorry about that. That's... there we go. That's the point of scale. That's the point of scale. Now, here's this beastly looking thing. Look, it starts at pi on 6. This is 13 pi on 6. Did we fit 4 cycles in? Yes, I think we did. We jolly well did too. Yes. So there's the point of scale. There it is. There's 1, 2, 3. They're all x-intercepts, and we've got the asymptotes labelled. And now we've just got to do the equation labelled, and we're done. We've done it, guys. We did it. Yes, we triumphed. Now, have we got any more of these beastly things? Oh, this is a vertically translated one. Gurky. Alright. Well, it's the same one as before, except that it's been vertically translated by root 3. So that makes it a bit easier for us, doesn't it? Alright, let's go. Okay, this is the same as the previous example, except the vertical translation of root 3 units. So that's the same, that's the same, that's the same. And the only diff, guys, is we've got this horizontal translation. Oh no, hang on. That's the same as before, but this is different. This one's different, isn't it? Yeah, vertical translation by root 3 upwards. Okay. Right, transformation refer above, working domain. Well, that was the same. It's the same as before. Starting point. Now, the starting point will be the same as the previous example, except that it's been vertically translated by root 3 upwards. Yes? So that'll give us pi on 6 and root 3 instead of pi on 6 and 0. Okay? Endpoints, same as the previous example, except they've been vertically translated upwards by root 3. So it's pi on 6, root 3. 13 pi on 6 and root 3. Endpoints, yes, except they're up by root 3. So that's the same as except they're up by root 3 as before. X-intercepts, now, these will be different from the previous example, but they will be the same distance apart as they were in the previous example. Okay, so we've got to work them out. Now, x-intercept means y equals 0. Now, therefore I'm solving you guys, aren't I? Yes? Now, that means, yes, that's the same as minus 1 over root 3. That's the way I think of them anyway. You might think of them as root 3 over 3, but I think of them as 1 over root 3. That's a pi on 6 basic angle. Pi on 6 basic angle, but we need it to be negative, so yes, but we need the negative quadrants. Which are they? That's the ones we want. Okay? Yes, good. Now, just recapping, over the working domain, what do we need? We need 2x minus pi on 3. Now, remember the working domain goes from 0 to 4 pi, doesn't it? Yes, working domain 0 to 4 pi. So here it is, right? We've got 5 pi on 6 from this one. We've got 11 pi on 6 from this one. And we're going to add 2 pi to each of those until we run out of working domain. Does that look about right? What's that? 12 and 11 is 23 on 6. Yes, that's very nearly 4 pi. So that's good. My oh my, I think we got it. There they are. Now we're going to solve it for x, guys. There's 2x. I've added pi on 3 to both sides, and now I'm going to divide by 2. There they are. They're the beastly little things. We worked them out, didn't we? So there they are. They're the x-intercepts, guys. Now, y-intercept, and we're nearly there. What do we got? No y. Oh, that's right, of course. No y-intercept, because we didn't have a... we started at where x was pi on 6. Point of scale, all hail, the point of scale. Same as the previous example, except the vertical translation of root 3. That gives us that. Yes, this is nice and easy, isn't it? Because we've done the previous example. We've done the hard yards. There it is. Now, you see how I've drawn the line in of y equals root 3. There, this is the label for it up there. So therefore, that's kind of like what the equivalent of the central axis being moved up by root 3. Yes, as we do in sort of sine and cos graphs, at least I do anyway. I think everything else looks pretty good, don't you? Let's see. There's the point of scale. That was a bit hard to work out, but I worked it out sort of with decimals, and then I sort of put it in about the right spot. Okay, so that's that one. That's the point of scale, and here, yeah, that's gone up by root 3. So vertical translation from the previous example, and these are our new x-intercepts. Look at them. The stars of the show, right? There they are. They're different from the previous example, but they are the same distance apart as they were in the previous example. So if you really wanted to, you could just work out one of these ones and then shuffle them across by the same amount as they were distant from each other in the untranslated up version, previous example. Right, what's that saying? Oh, yeah, that's the equation of the sort of central axis. You don't have to do that, by the way, but I would do that as a dotted line, just to show that it's not a main part of the graph, and you can't do that in this software, so sorry about that, but you should do it. If you're going to do it as a dotted line, yeah? Everything labelled, everything good? Oh, thank goodness, it's done. Now, what else have we got? Oh, here's solve an equation. I think this is the last one, guys. It's a long video, this one. We'll hurry up through it. This is just like the same procedure for a graph, except we don't have to do the graph, thank goodness. We've done enough graphs for a lifetime. And we just have to solve this, which means we work out a working domain. It's like working out x-intercepts kind of thing. The same sort of procedure, but we're not working out x-intercepts. We're just solving this equation, but we do work out a working domain. Here we go, I'll show you. Yes, if x goes from minus 2 pi to 2 pi, therefore what is all this stuff behind the tan symbol going to go from and to? We work that out, okay? We work it out. So there it is. There it is. I worked it out for you. That's our working domain. That's the domain within which we've got to capture our solutions, right? So solving for x, we've got that thing, haven't we? From up here, right? Yes. Now we're just going to get a basic angle, and we're going to fiddle with it within our working domain. So it's a basic angle of pi on 4, but of course it's -1, so we don't want quadrant 1, we want the negative quadrants. Yes, that's right, we want that, yes, yes. However, we want the negative quadrants, yes, which is those ones, yes. So in our working domain, ladies and gentlemen, moving backwards, we're moving, first of all, because we've got to go from a negative angle up to a positive angle. So I move backwards from 0 up down to that point there, and then I separately move forwards from 0 up to 9 pi on 8. Yes, here we go. Now we've got minus pi on 4. That's this one, right? I think that's all we've got, isn't it? Yeah, that's right. Secondly, in our working domain, moving forwards in the positive direction from 0 to 9 pi on 8. Now, 9 pi on 8 is just a little bit more than pi, so that means we're going to capture two solutions. Oh, no, we're not. Wait a minute. From 0 to... Oh, we're only going to capture this one, aren't we? Yeah, that's right. 3 pi on 4. We can't capture this one because that's a positive value. So we want the quadrant in which tan is negative. 3 pi on 4. Yes, very good. Now, I think that's it. Thank goodness for that. So, yes, yes, yes. Now we solve it for x, and then we're done. We're done, guys. And then we can go and have a cup of tea and get out of here. There's x minus pi on 4. Yes, and add pi and 4 to both sides, and we get, do we? Yes, we do, and that's it. Well, thank goodness, we just did Tan the Man in style, and you're a star and you'll go far, huzzah. Go and practice, and we'll see you next time. Thanks for listening, and bye for now.